War II. World War II. With secret Nazi anti-gravity, secret U.S. time travel, and the secret microwave oven. The V-1 killing M9 was Bell Labs' electronic gun director, the first non-mechanical gun aiming computer. The M9 used electronic computing devices to aim guns at fast-moving flying targets. The computational breakthrough was an amplifier that accurately added voltages and multiplied the result by a negative constant. Changing one resistor into a capacitor made it do calculus. The inventor, Bell Labs engineer Carl Schwartzel Jr., filed the patent application in 1941. Here's the schematic from the summing amplifier patent application. This is a stable, high-gain inverting amp controlled by a simple resistor network and is the birth of the operational amplifier, or op-amp, an amplifier that does mathematical operations. This simple tube circuit started a revolution in computing and automatic control. Op-amps could be interconnected in an electronic analog computer so that a complex mathematical problem could be solved by plugging in a few wires. Unlike the huge digital computers, a simple analog computer could be built with as few as 2 or 3 tubes. By the 1950s, the tubes could be replaced by transistors, getting smaller, cheaper, and more powerful. By the 1960s, the transistors could be replaced by integrated circuits, and hundreds of op-amps were flying to the moon. This is the circuit symbol for the modern op-amp. In addition to power wires, the amp has a negative or inverting input, a positive non-inverting input, and an output. The circuit ground, or common, is the midpoint between the positive and negative power to allow voltage outputs in both positive and negative directions. Here are some common op-amp circuits. The comparator. The op-amp can compare 2 voltages, snapping full up or full down when the voltages at the inputs differ by the tiniest amount. Here is the simplest feedback circuit, hooking the output directly to the negative input. In this circuit, the output accurately follows the positive input. Any difference between the output and the positive input is immediately corrected by the feedback. The input draws basically no current. The output supplies plenty. Putting equal input and feedback resistors on the negative input gives a unity gain inverter. The positive input is connected to the center of the supply voltage, or as they say, grounded. Because of the feedback resistor, the amp keeps the negative input the same as the positive at ground. To keep the negative input equal to the positive, the output resistor must lower by the same amount the input resistor raises. Think of an electronic teeter-totter. Here again is an op-amp with input and feedback resistors on the inverting input. If the feedback resistor is 10 times the input resistor, with 1 volt on the input, the output would stop at negative 10 volts. If the feedback resistor is 1/10 the input resistor, with 1 volt on the input, the output would stop at negative 1/10 volt. The higher the voltage gain of the amplifier, and modern op-amps have gains in the hundreds of thousands, the more accurate the result. The feedback resistor divided by the input resistor gives the gain of the circuit. Think of an electronic lever with the fulcrum at the negative input. Here we finally get to the 1941 computer breakthrough of the summing amp. With all resistors tied to the same point on one end, each resistor has a current exactly proportional to its input voltage. The currents all sum perfectly, giving an accurate sum of the input voltages as a current. All the summed current flows through the feedback resistor, giving multiplication of the total. For each input, the gain is the feedback resistor divided by the input resistor. Automatic control of servo motors and other systems is basic to most technology. The summing amp is the most basic form of controller. Two inputs are needed, a reference and a negative feedback. Voltage on the reference is summed with the negative feedback voltage, and the two subtract. When the two are equal, the amplifier output is 0. If anything changes, the amplifier drives things until the sum is again near 0. The feedback resistor on the summing amp is used to control the sensitivity of the controller. Too little gain, and the circuit is inaccurate. Too much, and the circuit is unstable. This is the amplifier which developed the gun control signal for the M9 gun director. The summer amp itself multiplies or divides the input by a negative constant. If the two numbers both change, that is, are variables, multiplication is more complicated. Several schemes, both mechanical and electronic, were developed for multiplying two variables. I believe the M9 had servo multipliers, motorized automatic control systems for multiplication. One number was input as voltage on the summing amp input. The amp's output controlled a servo motor with two potentiometers on its shaft. The feedback potentiometer fed negative voltage back into the summer so that the shaft angle was proportional to the first number's voltage. The other number was input as a voltage on the second potentiometer. The output of the second potentiometer was proportional to both the shaft angle and its input voltage, so it was proportional to the product of the two numbers. Putting a capacitor on the input and the resistor in the feedback gives a circuit which outputs the negative of rate of change of the input voltage. The faster the input voltage changes, the higher the output voltage. The M9 would have used this to calculate the rate of change of the tracker angles. Putting the capacitor in the feedback gives a circuit which calculates the negative running sum of the voltage. In calculus, rate of change and running sum are called derivative and integral. Enough said. It's time to look at the gun director in more detail. The gun director calculates how much the gun leads the target so the shell arrives where the target will be. The M9 had all sorts of inputs for its calculations: tracker horizontal angle, tracker vertical angle, wind speed, wind direction, latitude, air density, ballistic stuff, and I'm sure the all-important fudge factor knob. Here is the idea in simplest terms. An optical or radar tracker outputs the angle of the target. A circuit calculates the needed lead angle, which is summed with the tracker angle. The gun follows the sum of tracker angle and lead angle. An automatic control summer amp is used to drive the gun. The summer has 3 inputs, 2 positive and 1 negative. It has positive inputs from the tracker and lead angle calculator and negative input from the gun. In simple terms, the lead angle is the time of flight multiplied by the rate of change of the tracker angle. The time of flight is the target distance or range divided by the shell velocity. Here is a simplified circuit with summer, multiplier, and rate of change. The summer adds all the inputs together and outputs control to the gun. The rate of change circuit gives the rate of change of the tracker angle. The inverter changes the negative angle to positive. Multiplying the time of flight by the rate of tracker angle change gives the added angle. The time of flight is roughly equal to the distance divided by shell velocity. The operational amplifier is definitely something everyone should have in the toolbox. It has a lot more uses than the microwave oven.